Okay, let's take a seat, guys. Let's make a start. It's too dark. Okay. Right. So, let's move on to our new chapter, chapter 3. This one is again about the first law, because as I mentioned, the first law is so important that we're going to allocate chapter 2 and 3 on this particular law. So what we're going to be doing? We're going to be doing today in this chapter. We're not going to finish the chapter today, but we're going to finish this week. There are some important parameters in thermodynamics that we're going to be covering in this chapter. The first one is U. U is the intrinsic internal energy, which we're going to start today. Then we've got E, which is the internal energy, and we're going to see the difference hopefully today if you have time. We also have enthalpy. You might have come across H, which is enthalpy, and it's a very important parameter in thermodynamics. Has a lot of engineering applications. And also, we're going to be covering Cp and Cv. These are the specific heat capacities for at constant pressure and constant velocity. Again, you may have come across these before, but we're going to find out what they mean, how they're going to be defined, and how we're going to use them. Okay, so this is sort of the generic overview of what this chapter is about. Something that, if you remember in the last lecture, or in fact in the last chapter, we talked about the first law. And we related, if you remember the equation, we had delta U, or du, on the left-hand side. On the right-hand side, we had delta Q minus delta W. And I said U is a property, therefore we can use du. On the right-hand side, Q and W are not properties, therefore we have to use delta. We're going to come back to the numerical and mathematical representations of these parameters just in a few pages. But what we didn't really talk about, guys, quit it. What we didn't talk about last time was the actual meaning of heat and work. So we didn't actually spend a lot of time talking about the conventions, what work is, what heat is. Something which we completely ignored actually was the left-hand side of the equation, which is U. So what is this U, and why do we have Q minus W equals that internal energy? And this is what we're going to be covering today. When it comes to understanding the concepts of heat, work, energy, it's sometimes better to start from the physics, because in engineering, we can understand the implications and applications of these parameters, but then if you want to understand the meaning, you have to go back to the fundamental physics. So in quantum mechanics, which is one of the fundamental areas in physics, these are the sort of boring stuff that you will hear in Big Bang Theory, Sheldon talking about, quantum mechanics. That's the sort of stuff that they do in physics. We don't want to go really down that route because we have more interesting stuff to talk about. But when it comes to quantum mechanics, we really look at stuff and phenomena at a subatomic sort of level, and we look at the energy level at molecules and atoms. So it's really microscale that we look at. And in fact, for a moment, if you want to think about heat, and if you forget about the engineering meaning of heat, what heat really is the degree, or is a representation of a population of molecules and atoms in a certain part of a system. So if you have more population or bigger population of molecules in one part or in one system than another system, then you could potentially say that you have more heat in this system with a bigger distribution of molecules. But this is actually quite random, because it's a representation of the population of that particle, or atoms, for example. On the other hand, when you talk about work is actually more organized. It's not as random as heat, because if you think about work, you've got a cylinder, you've got a piston, and you've pushed the piston, and you're doing some work in there. Or you've got a propeller, for example. All you're doing is a sort of systematic change of of those particles. You are moving a series of particles from one location to another. Therefore, it's actually a more organized type of energy. Both, again, source of change of energy. It's a conversion of energy from one sort to another. But heat, let's call that a more random distribution, and work being a more organized type of energy. So what we also, for example, one of the things which we talked about last time was the zeroth law of thermodynamics. And we talked about, actually the fundamental part of the zeroth law is temperature, right? But then we didn't really talk about what temperature is. And we wouldn't talk about temperature until we talk about the heat, specific heat capacity, and that's actually when we understand what really temperature means. The same actually is with the internal energy. So remember, the focus of today is about U, which is the internal energy, intrinsic internal energy. And as far as that is concerned, the way that we want to define that really is a collection of potential and kinetic energy that a system might have, and that represents the intrinsic internal energy of that system. Now, we're going to see the mathematical representation of that in a moment, but as far as whether it's a property or not, and I know I've mentioned that actually a few times, but because the internal energy is path independent, so what I mean by path independent is when you think about the PV diagram, for example, the state diagram, it doesn't really matter what path you've taken. There's a certain value of U, and that is a property. As far as a system is concerned, that means that when a system has a certain amount of internal energy, it doesn't really care about, it doesn't have a knowledge of how it gained that energy. So it doesn't really know where it came from. You have a certain amount of energy, but it doesn't really matter how it gained that amount of energy, whether it was through heat, work, or any other sort of energy conversion. So we're going to be talking about this now a bit more using more equations, more formulas. But before that, let's just look at one formal definition of the first law of thermodynamics. So this is really just comes from the work by Joule in 1840 and 1848. That's the sort of period that he was working on this law. And in this box, there are a few fundamental aspects of the first law. The first is that it applies and it's defined within a cycle, and we're going to see why actually in a moment. And it's about heat and work, obviously, as you want to expect. So when a system executes a cyclic process, the algebraic sum of the work transfer is proportional to the algebraic sum of the heat transfer. So what does it mean mathematically? If you have, this is the amount of heat, so it's an integration of heat, and this C here corresponds or represents a cycle, or sometimes a closed contour. So that's what really C stands for. So what we know, and what this statement really tells us, is that the amount of work in a system has to be proportionate to the amount of work. Now, it's proportional to the amount of work in that system. If you want to set that equal to this one, of course you have to introduce a constant. Because when you say something is proportional to something else, you can't say they are equal unless you introduce an independent constant. In this case, for example, let's use J. And J is a constant, what we call mechanical equivalent of heat. And this allows us to convert heat to work and vice versa. Now, actually, this is going to be the only time when we're going to be looking at J and we're going to be even talking about it, because for the rest of the course, and potentially for the rest of your thermodynamics in this course, for the next 2-3 years, we're not going to really come back to J, because J has a value of, you can see the value here, it's a constant, and it actually has an imperial unit. But as far as you're working in SI units, then you don't really care about that, because J equals to 1 in conversion, which makes it a lot easier. And therefore, in any equation that you have J, you can then just ignore it. And therefore, a more simplistic way of defining the first law would never have J in there, as long as you're working with SI units. This is partially why I said, as far as you work with SI units, life is a lot easier because we're not working with conversions and imperial units, etc. So that is what the first law states as far as a cycle is concerned. Now, we talked about cycle. One thing which you might appreciate now is that, well, not all engineering problems and applications are actually in a cycle. You could have one sort of, if you like, a sort of a one-off or one-way process as well. And a typical example here is this airbag in a car. So this is certainly not a cycle. So does it mean that the first law is now not applicable to this? Actually, it gives you something interesting, because if you think about, well, first of all, the first law has to be applicable to this as well, because it's an engineering application, it's an engineering problem, an engineering design, and therefore these laws will be applicable to that as well. Now, if you think about this equation when it comes to the airbag, what it implies is that there has to be something else which would relate the work and heat, and that something else is the energy, is the internal energy which is stored within this airbag design, and it's actually released upon activation. And whether it results in work or heat or whatever, or both, that's a separate issue. But you can't define or you can't apply this equation unless you think about the role of the internal energy as well. And as long as you introduce the internal energy into the equation, then it's actually more applicable to a wider range of problems, including this non-cyclic process, which is the car airbag. Let's now go back to our cycle. This is a very nice and simple example of what a cycle is. Now, of course, we'll come back to a lot more complicated cycles towards the end of the course. But a simple idealistic cycle is like this. So what we have is, let's just say we have a tank and we have a fluid. Let's just say, it's just water. And you start introducing some mechanical work in this tank. For example, you start stirring it using a propeller or something. And if you think about these two diagrams, here I've got temperature and the specific volume, small v, and here we have temperature and pressure. Naturally, the temperature has to go up, because as you start doing this work inside the fluid, you know that the temperature of the fluid will rise. In this case, the pressure, because this is an open tank, you're not going to pressurize the water, or you're not going to pressurize this vessel. Therefore, the pressure is going to stay constant, and you're going to have a constant line, vertical line, which signifies that temperature is going up. When you look at the specific volume, of course, the temperature goes up. At the same time, the specific volume increases to some extent, because, again, looking at the quantum mechanics, the molecules at the subatomic level, they tend to expand as the temperature goes up. So you have a little bit of increase in the specific volume. Now, what if you start now, you put this tank, so this is actually this tank here. You now put the whole tank inside maybe just a container which has ice, or has a fluid which is a bit cold, in an attempt to reduce the temperature of your tank. This process, which you just saw there, will be reversed, essentially. You're going to be reducing the temperature, pressure is going to stay constant, and the specific volume is going to go back to the original state. So now you have completed your cycle. Another example, a very simple idealistic example, was the pump, which we saw in the last lecture. So what you could do, you had a cylinder, which was a sort of a simple pump. You could press and apply some force to the piston, and you could raise the temperature in the cylinder. Alternatively, you could just put a candle and raise the temperature. Either way, you are raising the temperature of this. And you could actually reverse the process as well, likewise. Now, something interesting about this is that you have introduced some work, and you raised the temperature, and then you took away the heat by cooling down, and you reversed that process. So step one, from 1 to 2, was a mechanical work. From 2 to 1 was just purely heat. What does it mean? As far as the system is concerned, there must be an equivalent, or a sort of a transfer which are equivalent between heat and work. Again, that's sort of emphasizing on the fact that these are the same thing. Work and heat come from the same principle, despite their differences. And they both would result in the change of state. And what I mean by change of state is moving from 1 to 2 or 2 to 1. That's what work and heat can both do. Let's now start looking at a more mathematical representation to derive something quite important. So I've got this cycle. Let's say I have one route which is AB. So I go from state 1 to 2 via A, and then we'll return via route B. Another option is to go via A and return via C. Now, I want to call the first cycle the red one, the blue one, 1A to B1, which just shows exactly the route. And simply, this is just really AB, if you like. And this one is naturally the AC type of route. This is a closed system. What I mean by closed, it means that you're not going to, you end up in the same state as you would where you started off. So, can we think about applying the first law to the first curve? If I do that, then I can write delta Q minus delta W for 1A2 plus the same for root B, delta Q minus delta W for 2BA has to be equal to 0. That's based on the first principle. This is based on what Joule has stated. I can do exactly the same thing for the red route. So again, exactly the same. Q minus W for 1A2 plus Q minus W for root C, which is 2C1, will be equal to 0. Because the right-hand side of both equations are the same, that means I can set this equal to this. Right? This is exactly what I've done here. I put them equal to each other. As a matter of fact, this will be cancelled. They're equal on both sides. And what you're left with the fact that this, or root B, has to be equal to root C in terms of the amount of work and the amount of heat which goes into or outside of these two curves. So we also know that neither delta Q or delta W is a property, and therefore mathematically let's just see what that means. It essentially means that because these are not properties, it means that the Q for root B and the Q for root C are not going to be equal to each other. Likewise, the work in root B and C are not going to be equal to each other as well. If Q and W were properties, this would have been different. But because these are not properties, therefore, they're not equal to each other. However, what that means is that the value of the combination of the heat and work will be equal to each other for root B and C. And that combination is important. So in isolation, you can't say that the amount of heat in either of these curves will be equal to each other, likewise for work as well, but when you combine them, they were actually equal to each other. This is exactly actually how we introduce that intrinsic internal energy. Because, and now let me just do a simple diagram to represent what I just explained. Let's assume that you've got this amount of Q, for example, for root B. And let's assume that you had this much of work for root B as well. And for now, let's just put that minus because mathematically then it makes more sense. But now I'm talking about the magnitude of heat and work. And let's just say that for root C, I had this much of heat. So let's just call this QC. And this much minus WC. I should have done this in red, but anyway. So what I mean is that individual components of heat and W might be different for those two roots, but when you combine them and you add them up, this magnitude is the same. And that magnitude actually is what we represent as the internal energy U. Does it make sense? Okay? And mathematically, this is where we define this one. Again, subscript 1 and 2 represent the initial and the final states. So you always start with state 1 and you end up in state 2. And if it's a cycle, then obviously you come back to state 1 eventually. And this change, or U2 minus U1, is what we call intrinsic internal energy. And this is slightly different to, for example, when we had E2 minus E1 in one of the equations earlier, where E actually here just represents internal energy, as we'll actually see this in more detail later on. Now, I want to draw your attention to three extensions, or if you like, corollaries of the first law. Now, when we introduce the second law as well, we're going to introduce a number of corollaries, which are just a fancy name for extensions or consequences or byproducts of that law. So these are the three which we've got here. The first one is about the fact that this corollary really just relates, when it comes to the change of state, it relates what we just mentioned, Q to W, and then both of them to the internal energy. So when you have a closed system and there's a change in the value or the change of state, then if you look at the net heat and work transfer, it has to be equal to the change of the internal energy. That's all it sort of states. Mathematically summarized in simple form in this equation. Corollary 2 talks about essentially the fact that the net internal energy will be equal to 0. So what it means is that the internal energy of a closed system remains unchanged if the system is isolated from the surroundings. So if you could somehow put your system in an isolated state, which means it's not in contact with, or it's not in exchanging heat or work with the surrounding, then the change in the internal energy is going to be 0. So your internal energy will be reserved essentially, or will be saved. And mathematically, therefore, the change will be 0, therefore your internal energy will stay constant. Corollary 3 is about what we call PMM, or the perpetual motion machine. I'm not sure if you've come across PMM in other engineering applications or in other subjects. We've got essentially 3 different types of PMM. This is just the first kind. I'm not going to go to discuss the other 2. It's an idealistic machine or system which can't exist, but it's an idealistic theory that if there was a machine which would be perpetual, which means it never ends, and it just produces work without any input. This is exactly what it means. Graphically, it's shown actually in this diagram. If you had a system, and this system was just giving you work without consuming any energy, that would be what we call PMM type of 1, or first kind. Corollary 3 really just states or proves that PMM 1 is just impossible. Of course, we all know that, but this is just from a thermodynamic point of view, this first law really states that this can't exist. Why? Because in theory, PMM would have no source of energy, so Q would be equal to 0. There's nothing to essentially add heat to the system. Therefore, we have Q equal to 0. And of course, because it's producing some useful work, your work will be positive. The net work will be positive. And when you look at the first law and the equation that we've seen so far, we have 0 for Q minus W12 equals U2 minus U1. Now, if I rearrange this equation and say, well, okay, now W12 is U1 minus U2, and if I know that W12 is really just infinity because it just gives you, it has unlimited amounts of work, then this one, U1, has to be an infinite source of energy as well. And we know that that doesn't exist. And as a result, PMM1 really can't exist, and this is the third corollary of the first law. Any questions so far? Now, you see lots of equations here, and the first thing you do, you panic. But this is actually quite simple, and actually a lot of it actually makes sense. The equations that we're going to be looking at here are probably one of the most important equations that you're going to be using, and probably one of the most fundamental equations as well. So it's good to understand where it comes from. This is really where we relate U to E, the intrinsic internal energy to the internal energy. Let's just start with our simple equation. In general, if you want to make this equation very generic, on the right-hand side of the equation, instead of having U, you must have E. Why? Because E actually includes U and a few other parameters, as you'll see in a moment. So what is the internal energy, or U? For now, just ignore the left-hand side. We know the left-hand side. We've looked at different variations. E2 minus E1, or simply delta E, is a combination of 3 elements. EP is the potential energy, EK is the kinetic energy, and U is the intrinsic internal energy which we introduced. And of course you can write delta EP, delta EK, etc. So why is it that sometimes you see on the right-hand side, you have U2 minus U1, and sometimes you see E2 minus E1? In a majority of the problems that we look at, because there's no change in potential energy and there's no change in kinetic energy, therefore these two terms, if they disappear, then essentially your delta E will be equal to delta U in the absence of the potential and the kinetic energy. And therefore, I mentioned last week that it doesn't really matter whether you put E or U. It's because if you think about, of course, if you want to be generic, then E is better. But in the majority of the problems that we're going to be looking at, we don't care about potential and kinetic energy. So that's just to get that out of the way, so that we know. Nevertheless, it's actually quite useful to define what is the kinetic energy and the potential energy. And I'm sure you all have covered these in different subjects. Half mv squared. V here is the velocity. It's not the specific volume or something else. So let's be clear on that. That is the kinetic energy. And if you want to look at the change in kinetic energy, because normally mass is constant, then it's just the difference between the velocity 2 minus velocity 1 squared. The potential energy is normally mgz, with m being the mass again, g being the acceleration due to gravity, and z being the elevation. And of course, the change in the potential energy will be the change in the elevation. Intrinsic internal energy is just simply U. It doesn't have an equation as such. It's not like kinetic energy or potential energy, because it's more of a physical definition, as a physical property. The only way that we can define it really is just by relating it to the capital U, which is the intrinsic energy, to small u, which is the specific intrinsic internal energy. And of course, the change is just m times u2 minus u1. Note that in all these three equations, you have m, m, m. And I'll come back to this in a moment. So let's just summarize all these and then expand the equation that we started with. I'm going now to change E2. This is E2, and this is E1 in an expanded format. And what I can do, I can just write this as in a small e, because small e represents the specific internal energy. The only difference being the mass again. So if you just be clear on this, that E, small e is equal to capital E divided by mass, okay? And if you want to express everything in specific values, then this is the simplest way of writing it. Small q minus small w equals small e2 minus e1. The only difference really being that when you work in specific values, everything is expressed per unit mass. And the units will change naturally because everything is going to be joules per kilogram. That's what you need to pay attention to. We're going to do one example here just to make sure that we understand. Because this equation is quite important, I want to make sure that you understand all the components in this equation in terms of both the units and the consistency as well. So, looking at this equation, I want to look at the quantities and the units for each quantity. Starting with the intrinsic internal energy U, because it's a small u, it would be joules per kilogram. The kinetic energy, as you can imagine, is velocity squared, therefore it's meters squared per second squared. The potential energy is g, which has the same units as acceleration, m second squared, and z, the elevation, is in meters, therefore you get meters squared s squared. When you start defining everything in the basic or in base SI units, then we know that each component has to have the same quantity and the same property. So the left-hand side, we have joules per kilogram, which represents heat and work. That is the same as Newton meter per kilogram. That's after you did redefine J, because J is not a base SI. In fact, Newton isn't a base SI either. Therefore, Newton will be changed to kilogram meter S squared. And when you do that, the left-hand side will be equal to meter squared second squared. The reason why I've gone very fast through this because we've done one example just 2 weeks ago on this specific one, and therefore you should all know this. But this just shows that the left-hand side has the units of meter squared second squared, and the right-hand side has the same meter squared second squared. Therefore, we are consistent. Some important points. These are just some tips. All the terms have to have the same or consistent units. You should not mix units. So if you use, for example, capital Q and capital W on the left-hand side, don't use small e or small u on the right-hand side. Either be in specific terms or just in general terms. And of course, don't confuse u with v and others because of different notations that we use for velocity, for internal energy, specific volume, etc. Now, what I want to do is to define, just a little bit expand on what we've been saying here about the first law, and talk about two different forms of how we express the first law. The first one is the integral form. You've seen this before. This is in an integration sort of format, therefore this is the integral form. Whether it's in general units or in a specific unit doesn't really matter, but what matters is that you've got the heat and the work in an integral. So that's fine, we've seen that. The next one is, it's probably more handy. This is the differential form. Now let's just look at the difference here. Everything is expressed in a differential form. Again, remember delta delta for work and W because these are not quantities, and D for the internal energy because the internal energy is a property. Now, why do we have to care about these two forms? I think it's more about this one and why and when we can use this format. There is a very good advantage of using this format. When you have, for example, certain values, or if you have state variables, and you want to solve that problem using analytical solutions, so you actually want to evaluate what is the value of work and heat, etc., in simple problems, this form, or this format, is actually a lot better and is a lot easier than the integral form. There's one caveat here, and that caveat is that you must make sure that your process is quasi-static. If you don't have quasi-static, then this form, you can't use this one. This equation is limited to that assumption. And of course, if you have, in the absence of kinetic and potential energy, this differential form is simplified to just delta Q minus delta W equals du. Why is it important to think about these equations and the differential form? It's because it allows you to start including some other equations that we've seen before. For example, this equation. When I was talking about displacement work, I said that this equation is a very common and simple equation. When you have work you can relate it to pressure and the change in the area or the displacement. PdV, where V represents that change of volume. In fact, now I can just replace delta W by PdV. And this equation actually is a lot more useful than this one. Because in a lot of situations where you have a moving part and displacement work, you don't have the value of work, therefore you can't just put it in there. But you might know the pressure and the change in the volume, and therefore that is a more useful form of equation. Again, one point to note is that if the process is not quasi-static, then that no longer applies, and therefore that analytical solution is not valid. However, that equation which we've seen so far, again, let's just be clear, that first law equation, Q minus W equals E2 minus E1, that is applicable to any type of problem, regardless of whether it's quasi-static or not. And that's why this is a more generic form of the equation, and it's essentially just re-emphasizes on the conservation of energy. The rest of this page, which talks about the rate forms of the first law, if you look at page, refer to page 2.2 in chapter 2, when we were talking about exactly the same thing. This is a point which I want to re-emphasize, because by now, some of you might be again confused about the use of delta and D, etc. The reason why we have D for quantity, for property, and delta for non-properties such as W and Q, is that in reality, so I can write du as u dot dt, again where u dot, or any quantity in thermodynamics with a dot, represents the rate form with respect to time. That is true, and it's true for any other property as well. If I write dq, this is not true, because of, again, on the fact that I mentioned that Q and W are not properties. And as a result of that, because this is not true, we have to stick to that notation of delta when it comes to the definition of Q and W. It's just, again, to re-emphasize on that fact. I know we've covered this before. This just here, just to clarify that.